Hello everyone, welcome to another lecture of linear control theory course. So today we are going to discuss about the closed loop control systems, and we will have a look at the steady state analysis of such systems. At the first part of the lecture we are going to discuss about the sensitivity functions. So you will see how the sensitivity functions are defined in it, and later we will see how they could be used in it, how useful they would be. So over here we have the standard closed loop system in the block diagram form that we are going to use throughout the course. You can see that a couple of signals are indeed determined here. R, which is the reference signal, then E, which is the error, N, which is standing for noise, U, which is the control variable, D, which is the disturbance, and C, which is the actual output or controlled output of the system. We can consider indeed R, N, and D as the inputs to the system, and E, U, and C as the outputs that we could get from the same system. Okay, so we have three inputs in the form of a reference R, sensor noise N, and the process disturbance D. And we have three outputs, which are the controlled output C, the control variable U, and the error signal, which is E. Then to analyze in order to start defining the sensitivity functions, we first define a transfer function which is called as the loop transfer function. The loop transfer function, which is shown by L of S, is obtained by multiplying GC, the transfer function of the controller, times GP, which is the transfer function of the plant. So indeed what we have here is this transfer function. Let me just change the pen. So over here we have the loop transfer function, which is GC times GP. Then, using L of S, the sensitivity functions are defined as you can see here. The first one is called the sensitivity function, and it's shown as S of S, capital S of S, and it's defined as 1 over 1 plus L of S. So S is equal to 1 over 1 plus GC times GP. And then we have the complementary sensitivity function, T of S, which is L over 1 plus L. It's called complementary because if you just do the addition of S plus T, you will end up with 1, and this is indeed shown here as well. So T of S is the complementary sensitivity function. And then the next sensitivity function that we have is called the control sensitivity function, and it is a little bit different than the previous ones. It's obtained as GC, the transfer function of the controller, over 1 plus L of S. Something to notice for these sensitive functions is that all of them have the same denominator. So at the denominator, there is the 1 plus L of S for all of them. So we have three sensitive functions, and they are the main sensitivity functions, and then the complementary sensitivity function, and then the control sensitivity function. Now, if you recall, we have indeed three inputs for this system. So this is one input, second input, and third input. And there are three outputs, error, the control signal U, and the controlled output C. If we apply the superposition principle, then the behavior of the whole system could be expressed in this matrix product format. On the left hand side, we have the outputs, in the form of a vector. And on the right hand side, we have the multiplication of a matrix by the vector of the inputs. So if I want to obtain the transfer function for, let's say, or the relation between one output and all the inputs for C of S, for example, C of S will be obtained as the first row of this matrix multiplied by the inputs vector. So T of S times R of S plus S of S times D of S minus T of S times N of S. How this is obtained, you can have a look over here. So let me just remove this. If you want to obtain the transfer functions between C, the output, and each one of the inputs, we apply the superposition principle. So each time you set two of the inputs to 0 and one stays there. Let me do it for the first case, where N and D are set to 0. So we assume that these are 0. And then we obtain the transfer function between C and R. So C over R could be obtained as what you see here. And this is a feedback init configuration. So we will have GC times GP over 1 plus GC times GP, which is indeed L over 1 plus L. And this is, as we already know, equal to T of S, the complementary sensitivity function. And then if I want to find the relation between C and D, I set N to 0, R to 0. Let me just redraw the block diagram system in order to make it easier for you to get. So here we have D with a plus sign here. And then after the adding point, summing point, we have C as the output. Then in the feedback pass, we have minus GC, GP, and with a plus sign here. So this minus GC that I just wrote here, this minus negative sign comes from here. Or we can just transfer it to the summing point. So if I redraw it again, we will have D with negative sign here, C over here, and then GC, GP of S. And if I want to find out the C over D, we will have in the feed forward we have 1, and as for the loop we have GP times GC, so 1 plus GC times GP, and this is equal to 1 over 1 plus L of S, and we know from the previous slides that it is equal to S of S. And finally, if I want to find the relation between C and N, noise, I will set D and N to 0. So we are going to find the relation between C and N. Okay. So if D and R are set to 0, we will have this situation. Let me just redraw. So this is 0, therefore this will be connected directly to here. I'm going to redraw the block diagram. N with a negative sign here. then GC, GP, D is set to 0, so we'll get C here. And then we have a negative sign here as well. So this time the negative sign that you see here comes from this sign. And well, by looking at it, you can see that it is quite similar to the case of C over R. The only difference is, let me just highlight it. The only difference is this negative sign. So C over N is indeed equal to minus C over R, which is equal to minus T of S. And you can see it here as well. So minus T of S times N. In this way, we can see that the sensitivity functions that we just defined could be used in order to give us an idea of how the different inputs are related to different outputs of the system.